Welcome back to our lecture series on structural characterization of materials. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In the previous lecture, we focused on how electrons are generated and why field emission sources provide such high beam quality. However, producing a high quality electron beam is only the first step. Once electrons leave the source, their usefulness depends on how well the microscope can preserve, shape, and control that beam as it travels down the column. This task is handled by electron optical system. Electron optics determines how tightly the beam can be focused into a probe, how the beam current is distributed, and ultimately what resolution can be achieved at the specimen. Even with an excellent electron source, poor beam control will severely limit imaging performance. In this lecture, we shift our attention from electron generation to electron lenses, which are the key components responsible for focusing and shaping the electron beam in a scanning electron microscope. Electron optics refers to set of techniques used to control the paths of electrons as they travel through the microscope column. The goal of electron optics are very similar to those of light optics. In both cases, we want to focus a beam, control magnification, and shape the beam so that it interacts with a specimen in a controlled way. The fundamental difference is that electrons carry electric charges. Because of this, electrons do not need glass lenses to change their paths. Instead, their trajectories can be manipulated directly using electric and magnetic fields. By designing appropriate field configurations, we can bend, focus, and shape electron beams with great precision. In the rest of this lecture, we will see how these fields are generated and how they function as electron lenses, forming the basis of beam control in scanning electron microscopes. Now that you understand that electron trajectories can be controlled using electric and magnetic fields, it is natural to ask what the simplest form of electron focusing might look like. The most basic way to control an electron beam is through electrostatic deflection. When electrons pass through an electric field, they experience a force that bends their trajectories. By shaping these electric fields using electrodes, it is possible not only to deflect electrons but also to focus them, forming what are known as electrostatic lenses. While electrostatic lenses are conceptually simple, a fundamental problem arises from how strongly their focusing strength depend on electron energy. Electrons with slightly different energies are bent by different amounts and therefore come to focus at different axial positions. This effect leads to a strong chromatic aberration, where the beam cannot be focused to a single sharp probe when there is an energy spread in the electron source. Since some energy spread is unavoidable in practical SEM operation, this severely limits achievable resolution. As a result, electrostatic lenses have only limited use in SEM beam formation. To overcome this limitation and achieve better probe control, modern SEMs rely primarily on magnetic lenses, which we will introduce next. After recognizing the limitations of electrostatic approaches, we now turn to the lens system that actually makes high-resolution SEM possible. When electrons move through a magnetic field, they experience a force perpendicular to both their velocity and the magnetic field direction. This is the Lorentz force. Rather than being pulled directly toward an electrode, electrons follow curved trajectories that can be precisely controlled. In SEMs, magnetic lenses are formed by passing current through a solenoid wrapped around a soft iron pole piece. This geometry concentrates the magnetic field near a small aperture, forcing electrons to spiral and converge towards the optical axis. Because magnetic lenses act primarily on electron momentum rather than directly on electron energy, they exhibit much lower chromatic aberration than electrostatic lenses. This makes them far more suitable for forming extremely small probes at practical beam currents. For this reason, magnetic lenses serve as the primary focusing elements throughout the SEM column, particularly in the condenser and objective lens systems that ultimately define resolution. A practical magnetic electron lens is built around a solenoid coil surrounded by carefully shaped iron pole pieces. When current flows through the coil, it produces a strong axial magnetic field concentrated in the narrow gap between the pole pieces. The role of the pole pieces is critical. They do not generate the field themselves, but they guide and confine it, shaping the field distribution so that it acts like a lens rather than a simple magnetic region. As electrons pass through this axial magnetic field, their trajectories bend smoothly towards the optical axis, leading to beam convergence. The strength of this focusing effect depends directly on the current supplied to the solenoid. By increasing or decreasing the lens current, we change the focal length of the magnetic lens without altering the beam energy. This ability to dynamically tune focusing using electrical current is one of the main reasons magnetic lenses dominate modern SEM columns. When an electron beam enters the magnetic field of a solenoid lens, the electrons experience a Lorentz force that bends their motion sideways. Instead of moving straight, the electrons follow spiral paths around the optical axis. Because the magnetic field is strongest and changing near the lens gap, these spiraling trajectories gradually bend inward. The combined effect of millions of electrons doing this simultaneously is a net focusing action, bringing the beam to a focal point below the lens. This behavior is directly analogous to how a convex glass lens focuses light rays. The crucial difference is that a magnetic lens has no moving parts. By adjusting the current in the solenoid, we change the magnetic field strength and therefore adjust the focal length electronically. The strength of a magnetic electron lens is not fixed. It is determined by several operating parameters that the user directly controls. The most important of these is the lens current. Increasing the current strengthens the magnetic field, causing electrons to bend more strongly and the beam to focus more tightly. The accelerating voltage also plays a key role. Higher energy electrons have greater momentum, so they are deflected less by the same magnetic field. As a result, increasing the accelerating voltage weakens the focusing action of a given lens current. Another critical parameter is the working distance, which is the distance between the objective lens and the specimen. A shorter working distance allows the beam to converge more tightly at the sample surface, producing a smaller probe. Increasing the working distance relaxes the convergence and increases the probe diameter. In practice, the final probe size is determined by the combined balance between lens current, accelerating voltage, and working distance. Optimizing these parameters is central to achieving high resolution or high signal, depending on the imaging goal. Before proceeding further, it is important to pause and look at a fundamental issue that limits how small an electron probe can be formed in practice. So far, we have discussed probe size largely in terms of the ideal electron optics, assuming that lenses focus all electrons perfectly to a single point. In reality, this is never strictly true. All real lenses introduce aberrations, which cause electrons traveling at different angles to focus at different locations. As a result, even a perfectly aligned lens produces a finite probe size. These aberrations represent fundamental limitations of electron optics, and they strongly influence spatial resolution in SEM. With that in mind, let us begin with the most important one, spherical aberration. Even in a perfectly aligned electron microscope, the objective lens does not bring all electrons to exactly the same focal point. This effect is known as spherical aberration. Electrons traveling close to the optical axis, often called paraxial rays, are focused differently from electrons that enter the lens at larger angles. The large angle rays are bent more strongly by the lens and therefore come to a focus closer to the lens, while the near axis rays focus farther downstream. As a result, instead of forming a single sharp focus, the lens produces a blurred focal region at the image plane. The size of this blur is referred to as the spherical aberration disk, and it represents the minimum probe size imposed by spherical aberration. Importantly, the size of this blur depends very strongly on the angular spread of the electron beam. The larger the beam convergence angle, the larger the spherical aberration disk becomes. In fact, the blur size increases with the cube of the convergence angle. This means that even a modest increase in beam angle leads to a very large increase in spherical aberration. The proportionality factor that sets the overall strength of this effect is a property of the lens itself, known as the spherical aberration coefficient. Because of this strong cubic dependence on angle, spherical aberration becomes a fundamental resolution limiting effect in round electromagnetic lenses. Although its impact can be reduced by carefully controlling apertures and operating conditions, spherical aberration cannot be completely eliminated in conventional SEM optics. After understanding spherical aberration, a natural question rises: how do we reduce its effect in practice? This is where aperture becomes important. An aperture is a physical opening placed in the electron optical column that limits the maximum angle at which electrons can reach the specimen. By blocking electrons that travel at large angles, the aperture removes the rays that contribute most strongly to spherical aberration. As a result, the beam reaching the specimen has a narrower angular spread, leading to a smaller aberration disk and improved spatial resolution. However, because fewer electrons are transmitted through the aperture, the total beam current is reduced. At this stage, it is important to recognize apertures as a tool to improve resolution by controlling ray angles. In the next slide, we will see that this solution, while effective, comes with its own fundamental limitation. Up to this point, apertures appear to be an effective solution for reducing spherical aberration. However, the same aperture introduces a new and unavoidable problem. Electrons are not only particles, they also exhibit wave-like behavior. When an electron passes through a finite aperture, diffraction occurs, just as it does for light passing through a small opening. As a result, even if the lens were perfect and all aberrations were removed, the beam would still not form a perfect point at the image plane. Instead, it spreads into a diffraction pattern with a central bright region known as the airy disk. This diffraction effect broadens the probe size. Importantly, the smaller the aperture, the stronger this diffraction spreading becomes. This creates a fundamental trade-off. Reducing the aperture suppresses spherical aberration, but it simultaneously increases diffraction. Therefore, apertures solve one problem but introduce another. The final probe size is determined by a balance between these competing effects. The contribution from a spherical aberration increases very rapidly with aperture angle. Specifically, the spherical aberration disk size is given by ds equals cs times alpha cube. This cubic dependence means that even a modest increase in the beam convergence angle leads to a much larger aberration blur. In contrast, the contribution from diffraction behaves in the opposite way. Because electrons have wave nature, the diffraction limited probe size is given by dd equals 0.61 times lambda divided by alpha. This tells us that reducing the aperture angle increases the diffraction blur, while increasing the aperture angle reduces diffraction effects. As a result, spherical aberration and diffraction compete with each other. Increasing alpha helps diffraction but worsens spherical aberration, while decreasing alpha suppresses spherical aberration but worsens diffraction. The smallest achievable probe size therefore occurs at an optimum aperture angle, where these two effects are balanced. This balance between aberrations and diffraction represents a fundamental limitation of electron optics and plays a central role in SEM probe formation. In addition to spherical aberration, electron lenses also suffer from chromatic aberration, which arises due to the finite energy spread of the electron beam. Not all electrons emitted from the source have exactly the same kinetic energy. Because the focusing strength of a magnetic lens depends on the electron velocity, electrons with different energies are focused at different axial positions. Higher energy electrons are bent less and focus farther away, while lower energy electrons are bent more strongly and focus closer to the lens. As a result, instead of forming a single focal point, the beam exhibits an axial spread of focus, which increases the probe size and degrades the resolution. Chromatic aberration is particularly sensitive to the quality of the electron source and the stability of the accelerating voltage. Field emission sources produce beams with a very small energy spread, and a stable high voltage supply ensures that this energy does not fluctuate during imaging. Both are essential for achieving high resolution SEM performance. To summarize our discussion so far, an ideal lens would focus a point object to a minimum size. In practice, this ideal situation is never achieved. Real lenses suffer from multiple broadening mechanisms. Spherical aberration causes rays at different angles to focus at different positions. Diffraction imposes a fundamental spreading due to the wave nature of electrons. Chromatic aberration further broadens the focus because electrons with different energies are focused differently. As a result, the actual focused spot size is larger than the ideal value. A useful way to think about this is that the final spot size is a combination of all these independent contributions added in quadrature, as shown in the expression here. This relationship highlights an important idea. Improving focus is not about eliminating a single effect, but about managing several competing limitations simultaneously. Before we discuss how lenses are used together in an electron optical system, let us briefly review the basic ideas of magnification and demagnification from geometric optics. These concepts apply equally to light optics and electron optics. For a thin lens with focal length f, the object distance and the image distance are related by the thin lens equation. The magnification is defined as the ratio of image distance to object distance. In many optical systems, we are interested not in magnifying an object, but in reducing its image size. This process is called demagnification and is simply the inverse of magnification, given by the ratio of object distance to image distance. These basic geometric relationships describe how lenses change image size. We will use this same idea when we later discuss how multiple lenses are combined to control beam size and focusing in electron optics. In an SEM, the electron beam is not shaped by a single lens. Instead, the microscope uses a two-lens system to form and control the probe. A condenser lens system followed by the objective lens. Think of the process in two stages. First, the condenser lens system shapes the beam before it reaches the objective lens. Its main job is to control how strongly the beam is prepared for final focusing. In practical terms, the condenser setting strongly influences three things at once. One, how much beam current is allowed to pass downstream. Second, the beam diameter crossover size entering the objective lens. And third, the convergence angle of the beam that will eventually form the probe. Second, the objective lens performs the final focusing onto the specimen. This is the lens that directly determines the working distance geometry and strongly affects the final probe shape at the sample. Now, as an operator, you don't directly tune spherical aberration or diffraction as separate knobs. Instead, you control parameters that indirectly change the angular spread and focusing geometry, and therefore change how strongly these limits show up in the final probe. That is why these three operator controls matter so much. First, objective aperture size. It sets the maximum accepted ray angle, cutting off high angle electrons. That reduces spherical aberration contribution, but if pushed too small, it increases diffraction effects. Second, working distance. It changes the objective lens geometry at focus and typically changes the effective convergence conditions at the specimen, influencing probe size and resolution in very practical way. Next, condenser lens strength, which controls the illumination conditions, mainly the trade-off between beam current and the beam's angular size conditions entering the objective lens. So the big message is, probe formation is the outcome of both lens systems working together. Your settings are essential. Choosing a practical operating point, how much current you want, what probe size you can tolerate, and what imaging conditions are the best for the sample. One of the practical tools available to the SEM operator is the use of objective aperture. The objective aperture is a physical opening placed in the electron optical column near the objective lens that limits the maximum angle at which electrons can travel toward the specimen. By restricting high-angle electrons, the objective aperture selectively removes rays that contribute most strongly to lens aberrations. As the objective aperture size is reduced, the angular spread of the beam decreases, leading to a smaller aberration disk and improved spatial resolution. At the same time, fewer electrons are transmitted through the aperture, resulting in a reduced beam current. The objective aperture therefore provides a practical means of controlling the trade-off between probe size and beam current by regulating the range of ray angles allowed to participate in image formation. The working distance, or WD, is defined as the distance between the objective lens and the specimen surface. It is one of the most important operator control parameters in an SEM. When the working distance is short, the objective lens operates more strongly to focus the beam. This leads to a smaller probe size at the specimen and therefore better spatial resolution. As the working distance is increased, the lens focuses the beam more weakly. The probe arriving at the specimen becomes larger, which reduces resolution, even if all other conditions remain unchanged. Working distance also affects depth of field. A longer working distance increases depth of field, which can be advantageous for imaging rough or highly three-dimensional samples. But this comes at the expense of probe size and resolution. Therefore, the choice of working distance represents a practical trade-off between probe size, resolution, and imaging geometry and must be selected based on the imaging goal. This slide shows how changing the condenser lens strength affects the electron beam before it reaches the specimen. On the left side, we have a weaker condenser lens. Because the condenser is weak, the beam is not tightly focused upstream. As a result, fewer electrons are delivered to the specimen, giving a lower beam current. At the same time, the beam arrives with a smaller convergence angle, meaning the rays are more nearly parallel. This condition is often preferred for high-resolution imaging, because the smaller convergence angle reduces aberrations and improves probe definition. On the right side, the condenser lens is stronger. The beam is focused more aggressively before reaching the objective lens, which increases the beam current. However, this also produces a larger convergence angle with electrons arriving over a wider range of angles. While the higher current improves signal strength and image brightness, the larger convergence angle can increase aberrations and limit ultimate resolution. In practice, the condenser lens is one of the main controls the SEM operator uses to balance beam current, resolution, and image quality. After shaping and focusing the electron beam using lenses and apertures, the next essential function in an SEM is to move that focused probe across the specimen surface. This task is performed by the deflector system, often implemented as electromagnetic scanning coils located above the objective lens. The deflectors do not change the beam's focus or size. Instead, they apply controlled electric or magnetic fields that slightly bend the electron trajectory, allowing the beam to be positioned precisely on the sample. By driving the deflectors with time-varying voltages or currents, the beam is scanned in a raster pattern, line by line and point by point, across the specimen surface. At each beam position, emitted signals such as secondary or backscattered electrons are collected and assigned to a corresponding pixel. In this way, the spatial variation of signal intensity is converted into an SEM image. Importantly, magnification in SEM is not set by lenses, as in optical microscopy, but by the scan amplitude of the deflectors. Reducing the scan area while keeping the display size fixed increases magnification. Thus, the deflector system plays a central role in image formation by controlling where the beam goes and how the scanned image is constructed. In an optical microscope or a transmission electron microscope, an image is formed almost instantaneously by focusing rays onto an image plane. The scanning electron microscope works in a fundamentally different way. In SEM, there is no pre-existing image plane where the full image suddenly appears. Instead, the image is constructed sequentially, one point at a time, as the electron beam is scanned across the specimen. The beam follows a precise and repeatable pattern known as raster scanning. It sweeps rapidly back and forth along one horizontal line, the fast scan direction. And after completing each line, it steps downward slightly to begin the next line, the slow scan direction. At every instant in time, the beam occupies a specific position on the specimen. From that position, the specimen emits a signal such as secondary or backscattered electron, and the intensity of that signal is recorded. That signal intensity is then assigned a brightness value on the display. In this way, time is converted into position and position is converted into brightness. This is why scanning coils are so important in SEM. They do not form the image themselves. Instead, they define where the beam is at every moment. The image emerges gradually, point by point and line by line as the scan proceeds. A very useful concept for understanding image formation and resolution in the SEM is the idea of the pixel or picture element. An SEM image is not continuous. Instead, it is made up of a large number of discrete pixels arranged in a grid. Each pixel corresponds to a specific position of the electron beam on the specimen during the scan. When the beam dwells at that position, the emitted signal is measured and assigned a brightness value to that pixel. It is important to recognize that a pixel in SEM is not merely a digital display element. It represents a physical sampling of the specimen at a particular location. In other words, the pixel defines where the material is being probed and how finely the specimen is sampled. This idea will be central when we talk about resolution and image quality. In an SEM, the movement of the electron beam across the specimen is directly mirrored by the signal on the display. Each beam position corresponds to a single pixel on the screen, establishing a one-to-one mapping between specimen pixels and screen pixels. An important point is that SEM images always contain a finite number of pixels. In early analog SEMs, the amplified detector signal was displayed on a cathode ray tube or CRT. The smallest spot that could be formed on the CRT limited the image to roughly 1,000 pixels in each direction. Modern digital SEMs no longer use CRTs. Instead, images are stored in digital frame buffers. While the technology has changed, the pixel sampling principle is exactly the same. The image still contains a fixed number of pixels. Increasing the pixel does not increase the number of pixels in the image. It simply maps a smaller region of the specimen onto the same fixed pixel grid. This is why SEM magnification is fundamentally different from optical magnification, and why resolution cannot be improved by zooming alone. We can now quantify how magnification affects sampling in the SEM. Here, P represents the specimen pixel size, the physical area on the specimen that corresponds to a single pixel in the image. It is important to note that this pixel is not a real feature of the material, but a sampling unit imposed by the microscope. If we assume a typical display size of about 100 microscopes per pixel across the screen, the specimen pixel size scales inversely with the magnification, leading to this simple relationship. The key point is the trend rather than the exact number. As magnification increases, the specimen pixel size decreases. In other words, each pixel represents a smaller region of the specimen and the sampling density increases. However, there is an important limitation imposed by the sampling. The specimen itself is continuous, but the SEM samples it at discrete locations defined by the pixel grid. Each specimen pixel, therefore, represents an average signal over a finite area, not an individual physical feature. If two distinct features lie within the same specimen pixel, their signals are averaged and they will be recorded as a single point in the image, regardless of how good the electron optics are. This is why magnification alone does not guarantee improved resolution. Resolution in SEM is always limited by both sampling, determined by the pixel size, and probe size, which we will discuss next. Having quantified how magnification controls the specimen pixel size, we can now look at how pixel size and probe size work together to determine image quality in SEM. The electron probe has a finite size set by the electron optics, while the specimen pixel size is set by how finely we sample the image during scanning. What matters in practice is how these two length scales compare to each other. If the probe size is larger than the specimen pixel size, the electron beam interrogates multiple neighboring pixels at once. Signals from adjacent regions become mixed and the result is a blurred image, even though the sampling rate may be fine. On the other hand, if the probe size is much smaller than the specimen pixel size, each pixel receives signals from only a very small fraction of the beam interaction. The signal per pixel becomes weak and the image appears noisy, even though the probe itself is small. Optimal imaging occurs when the probe size and the specimen pixel size are comparable. In this case, the beam interrogates roughly one pixel at a time, maximizing both spatial fidelity and signal to noise ratio. Importantly, the operator controls both of these quantities. Probe size is adjusted through choices such as objective aperture, condenser lens strength, and working distance. Specimen pixel size is controlled through magnification, scan area, and the number of pixels used to record the image. This balance between probing and sampling is why SEM imaging always involves trade-offs and why optimizing image quality requires coordinated control of both electron optics and scanning parameters. Now that we understand how an image is formed in the SEM point by point, we can examine what actually limits resolution in practice. In SEM, two features can be resolved only if they occupy different pixels in the image. If two features fall within the same pixel, their signals are averaged and they appear as a single feature. This immediately tells us that SEM resolution is limited by more than one factor, and it is important to distinguish between them. The first factor is pixel size, which is determined by scanning and sampling process. Specifically, the scan area and the number of pixels used to record the image. Pixel size defines how finely the specimen is sampled. The second factor is probe size, which is determined by the electron optics, including the lens system apertures, and working distance. Probe size defines how finely the electron beam interrogates the specimen. However, even when both sampling and probing are optimized, there is a third fundamental limitation: the electron-sample interaction volume. The detected signal does not originate from a single point, but from a finite volume within the specimen where electrons scatter and generate signals. These three factors, pixel size, probe size, and interaction volume, interact with one another to determine the practical resolution of an SEM image. Improving one factor cannot compensate for limitations in the other. Fine sampling cannot recover information lost to a large probe or a large interaction volume, and a very small probe cannot overcome coarse sampling or deep signal generation. This is why SEM resolution is not the same as magnification. Increasing magnification alone does not improve true resolution unless the optics, the sampling, and the physics of beam-specimen interaction are all appropriate. So far, we have discussed the first two factors, pixel size and probe size, in considerable detail. In the next lecture, we will focus on the third factor, the interaction volume, and how it ultimately controls where SEM signals originate and what information they carry.